Hi there. So in this module, we are going to take a look at the voltages, currents, and the symbol of metal oxide semiconductor field effect transistor. That is a MOSFET, or simply it is called as MOS. So we know that there are devices such as BJT, JFET, and third one is the MOSFET. So for the first previous two, we have given the tutorials on that, so refer to that. Now, there are two types of MOSFET. One is called N-channel and one is called as P-channel. Now, how to distinguish between the two? So that is possible by drawing the symbol and knowing the direction of current flow through the device. So what I do here, I will draw the symbol. It is a 3-terminal device. So as you can see, this is a terminal called gate. This is a terminal called drain, and this is a terminal called source. Now, what I'll do here, I will draw and tell you the voltages and the currents. The voltage at this terminal is called as drain voltage. The voltage at this terminal is called as source voltage. And the voltage at this pin or terminal is called as gate voltage. Current flowing into the gate is called as gate current. Current flowing into the drain is called as drain current. And current flowing through the pin source is called as source current IS. And important part here is to understand there is a 1/4 terminal or fourth pin to the MOSFET also. So it is therefore also called as body type MOSFET, and the body is the fourth pin. And you can see that I have now drawn the arrow right here that indicates the direction of the current flow, and therefore it is called as N-channel MOSFET. Okay. So you see that the current flow is from drain to source. Okay. And the arrow indicates that the current is going inside the pin right here. Now there are voltage polarities that I want to draw here. So the voltage across gate and the source with source positive is called as VGS. The voltage across gate and the drain with drain positive is called as VGD, that is gate to drain voltage, and the voltage across the drain to source is called as VDS with drain positive. How can we draw the symbol for the PMOS now? It is pretty simple. As you can see that this is how I will draw. This is terminal pin gate. This is drain, and this is the source. And the fourth terminal, which is a body terminal, will be drawn like this with the arrow pointing outwards. So that indicates your P-channel MOSFET. Let us draw the direction of the currents. The current, drain current will be drawn like this. The source current will be drawn like this. And the gate current will be drawn like this. With the voltages like this, where VD is the drain voltage, VS is the source voltage, and VG is the drain voltage. Now, how about the voltage drops? Just like we drawn here. So the polarities, the voltages will be same as in N channel with the polarities. reversed. For example, you have a negative and a positive here. You will say that gate is positive with respect to drain, and the voltage will be written as VGD. Here, the voltage will be negative and voltage will be positive. It will still be called as VDS. Here, you have positive and the negative. Gate is positive and the voltage is called as VGS. Okay. Now, there is some terminology for the MOSFETs. We say that the gate current IG. Let me use the different colors for better understanding. We say that the gate current is approximately 0 ampere. Why? Because for a MOSFET, metal oxide semiconductor, gate is insulated so that the input current is negligible. Okay, remember you have a MOSFET, so you have a metal, this is your metal, this is your oxide, and this is your semiconductor. So the current cannot flow through the oxide ideally. That's why we call it gate current is equal to 0, because the current cannot, this is your gate terminal, so current cannot tunnel through the oxide. And second terminology, we say that ID is equal to IS. So drain current is equal to source current. That indicates the device is symmetric. Okay. Now, there are two regions of operation, just like JFET in a previous model. We saw the input curves and the output curves, or input characteristics and the output characteristics. So there are equations to define the operation of the current, operation of the transistor in those regions. One is called as linear region. We'll see in a moment. And one is called as saturation region. So let me write down the equations for the drain current in those two regions. So the first equation is the drain current in the linear region. It is given by mu n C ox W over L in bracket VGS minus VTH into VDS minus VDS square divided by 2. And this is your current expression in the linear region of the operation. In a moment, I will define the terms. For example, what is mu, what is Cox, what is WL, etc. Okay, so now we will write the expression for the drain current in the saturation region. So we can write the expression of the drain current in the saturation region as shown, mu n into Cox divided by 2 W over L VGS minus VTH whole square in bracket 1 plus lambda in bracket VDS minus VD sat and bracket close. So this is the expression of the drain current in the saturation region. Now, what are all these terms mean? So for example, we say that mu n is called as carrier mobility. So you see, when the electrons and the holes, which are the charge carriers that flow through the semiconductor device such as MOSFET, their mobility, or in other words, their speed of conduction is called as carrier mobility. Cox is called as oxide capacitance. Now, what is capacitance, oxide capacitance? Remember, you have metal, then you have an oxide, and then you have a semiconductor. So essentially it is a capacitor C. You have, that's why we call it metal oxide semiconductor MOS. And that gives rise, the two plates of the capacitors are the metal and the semiconductor, and in between oxide acts as a dielectric. Now, what is W and L? That is width and length of the device. So your MOSFET is basically a three-dimensional device. So you see that there is a width. This is called as length of the device. That is the channel length. And here is called as width of the device. So it defines the cross-section of your transistor. Bigger the device in the width, large is the current flowing through this. Okay, now let me define some more terms that we have seen. VGS and VDS, we already know that VGS is gate to source voltage. VDS is drain to source voltage. Now lambda is channel length modulation. Okay, so that's the parameter that modulates your channel length. And your VTH is called as threshold voltage. Threshold voltage of the transistor, of the MOSFET. So remember, when you apply a gate voltage, this is your VG, on the top of the metal oxide and the semiconductor, when you apply VG, there is a channel inversion. And until the channel inversion is reached, you need to keep increasing or applying this voltage. So the moment your channel inversion happens under the MOSFET, that voltage is called as threshold voltage. So MOSFET is said to be turned on when VG with respect to source is greater than the threshold voltage VTH. Okay, so we have defined all the terms for the transistors, and we have seen that symbol of the transistor, how it works. Now it's time to take a look at the output characteristics of the transistor and the input characteristics of the transistor. So we will draw the curves to understand the output characteristics of the MOSFET. It is pretty similar to the output characteristics that we drawn for the junction field effect transistor earlier. So let me draw that for you. So right here, what we'll do, again, the output characteristics or output curve, which is a curve between ID, that is the output current, versus the output voltage for the given values of input voltages, that is VGS. And we will draw it for N-channel MOSFET. Remember, the characteristics will be same for the P-channel MOSFETs with the polarities of the voltages reversed. So let us draw that. So on the y-axis, you will have a drain current, ID, which is in the milliampere usually. On the x-axis, you will have drain to source voltage, VDS, which is in the volts. You start with 0, and then you have values of the voltages 2, 4, 6, 8, 10, and so on. And then you say, I want to draw the current relationships for the applied values of the voltages. So you start with, let's say, a very small value of VGS. Let's say VGS equal to 0.5 volt. Then when you apply the input voltage, and for increasing values of VDS, current starts increasing. But after that, your current is saturated because the channel is pinched off. Let me draw it properly. Your channel is pinched off. That's why the current is saturated. So you say that this is for the VGS is equal to 0.5 volt, for example. Now next, again, you increase the VGS, let's say from 0.5 volt to 1 volt. So naturally, when you then increase the VDS, your current also increases. Okay, but current is increasing mainly due to increasing the VGS. But if you increase the VDS, then afterwards, your current is saturated. So this is how the MOSFET behaves. VGS equal to, let's say, 1 volt. Again, you will see that for larger values of VGS is equal to, let's say, 2 volt, your current is increasing linearly, but after that, for larger values of the VDS, your current is saturating at this point, at this point, at this point. Let's have one more curve here. So let's say this is VGS is equal to 4 volt or 3 volt, for example. And finally, you will say that this is, let me draw it nicely so that you can actually understand it better and better. Well, this is not easy to plot the curves with hands, but it's still understandable. So VGS is equal to 4 volt. So you see, for the positive values of positive values and increasing values of the VGS, your current is increasing initially, and after that, your current is saturated. Now here, there is one important term or important regions that we will indicate. We'll say that we'll draw the line, and the area left to this region or left to this line is called as linear region of the MOSFET operation, and the area right to this line is the region which is called as saturation region of the operation. It is important to note that the parameters such as the mobility, oxide capacitance, then width and the length may not be given in the datasheet of the MOSFETs. Okay. Second point is, this is for the N-channel. This is, as I said before, this is your N-channel MOSFET output characteristics, output curve, which is ID versus VDS for a given values of the VG. What would be the output characteristics for the P-channel MOSFET? That's an exercise for you. Hint is, the P-channel MOSFET will have a similar characteristics curves, but the polarity is opposite. For example, the VDS, values of the VDS will be negative values, values of the VGS will be negative values, and the drain current accordingly will be drawn. So hope you understood the voltages, currents, symbols, and the direction of current flow of the MOSFET and its output characteristics. You also understood, as I explained to you before, the region of operations are linear region of operation, and in each linear region and the saturation region, I have given you the current expression. Remember, the drain current ID is having a different form of expression in the linear region, and the drain current ID has a different expression for the operation in the saturation region. If we say that channel length modulation is another parameter, we'll cover that somewhere in other module. If that is termed to be 0, then this term goes to 0. And then the expression is just up to this. So this is called as the shorter form of your expression for the ID. Okay, so that's all for the MOSFET for this particular module. We are going to see more details on the MOSFETs, the physics of the devices in some other modules. Till then, stay tuned. If you like the video, do share with others, like it, comment on it, and share it with others. And stay tuned. Till then, wish you happy learning.